Hello everyone. In this video and the following two example videos, we'll take a closer look at Newton's third law of motion. Newton's third law states that if object A exerts a force on object B, an equal but opposite force is simultaneously exerted by B on A. This is sometimes called the law of action and reaction. So if a force is exerted on B, it exerts an equal and opposite force on A. Notice that in Newton's third law, there are only two objects involved, and the forces come in pairs based on those two objects. We can go on to find other pairs based on two objects or even the same two objects, but we deal with one pair at a time. And those two forces in that pair are always the same type of force: gravity and gravity, contact and contact. Here are some examples of Newton's third law in transportation. So when you're walking and you exert a force on the ground, or your foot exerts a force on the ground, or the ground exerts an equal and opposite force on you. So notice we've got the two separate objects here. So I'm drawing them a little bit different than what's there because I want to emphasize the two different objects. In B, the propeller exerts a force on the water, and the water thus exerts a force on the propeller attached to the boat, which is what helps propel you forward. Likewise, for a rocket, the rocket exerts a force on the gases, a downward force, and those gases then exert an equal and opposite force on the rocket, which propels it upwards. And in the wing, example of the wing for flight, we have the wing exerting a force on the air, and the air exerting a force on the wing to lift it. Let's look at another example where we're looking at a single object and multiple forces. So we saw this box earlier. Let's use it as an example. I pull a box to the right. What is the reaction here? So I'm pulling on the box to the right. That means the box is thus pulling on me in the opposite direction. A box pushes down on the ground. So the box exerts a force on the ground, and the ground exerts a force upward, that normal force. Earth's gravity pulls the box down, so now we have the gravitational pull on that box, and so the box pulls the Earth back. Now, while this might seem a bit strange, the 10 Newton force on the box is quite significant. But indeed, the box does have a gravitational pull on the Earth. It's just that that 10 Newton force on the Earth doesn't achieve much and isn't really noticed. But they are the third law pair in this case. There's a gravitational pull each way. And so it's important to notice that the normal force and gravity that you see acting on that box are not third law pairs. So the normal force that we see acting upward and the gravitational force that we see pulling it downward are not third law pairs. They often are equal and opposite for an object that's on a flat surface, but they're acting on the same object. The normal force acts on me or on the box, gravity acts on me or on the box, and so they cannot be a third law pair. We saw these examples earlier. We looked at this example where we had a brick and a walnut. And so this shows you the action-reaction pair. For that force of gravity on the brick by the Earth, there's an equal and opposite force of gravity on the Earth by the brick, and likewise for the walnut. Let's look at this example that demonstrates Newton's third law. A figure skater of mass 56 kilograms pushes horizontally against the boards at the side of a skating rink for 0.75 seconds. Having started at rest, she leaves the boards with the speed of 75 centimeters per second. You can neglect friction and are asked, what were the magnitudes of her acceleration, the force exerted on her by the boards and the force that she exerted on the boards. If we look at the free body diagram for the skater, there's a force exerted in one direction for her. This is the force exerted on the skater by the boards. Well, she exerts a force equal and opposite on the boards by the skater. And so the force on the skater, there's only a single force here, the force of her pushing back against the board, because we're told we can neglect friction. Now, that's only the only force in the x direction, I should say. So we do have a normal force, and we do have the force of gravity, and we expect those to balance out in this case to keep her in equilibrium in the y direction. So I'm defining this as my positive y, and I'll define this direction, I'll put it here so I'm not overlapping, as my positive x direction. And so I've got a mass for the skater here of 56 kilograms. And now we're given a bit of kinematics. So we're told that the delta t, or t minus t naught, is 0.75 seconds. That she applies this force. She started at rest, so we have a v naught equal to 0. And she leaves the board with a speed of 75 centimeters per second. And I've indicated that this is my positive x-axis. Therefore, if she's going in this direction, this is going to be a negative v. So I've got a negative 75 centimeters per second in this case. And I'm going to convert that then to meters per second. So I get a negative 0.75 meters per second. The acceleration is unknown, and that's one of the things we're trying to find. And the force on the skater by the boards is unknown, and the force on the boards by the skater is unknown. So this is really part A. Force exerted on the skater is part C, and the force exerted on the boards is part B. For part A, this is simple kinematics, where we know we can use this equation involving velocity and time. Initial velocity is 0. So let's solve for that acceleration as v over t. We have a negative 0.75 meters per second over 0.75 seconds. And so we learn that we've got a negative 1 meter per second squared acceleration. And so the magnitude of that is the 1 meters per second squared. The negative tells us the direction. And we're asked here for the magnitudes. So that was A. Part B then, find the force exerted on her, the skater, by the boards. We know her mass and we know her acceleration. And so the force of on the skater by the boards is going to be a negative 56 newtons because it's to the left. It asks for the magnitude, and so that's 56 newtons. Lastly, the force that she exerted on the boards, so on the boards by the skater, must be equal and opposite by Newton's third law. And so it's a positive 56 newtons, and so the magnitude of that is then also 56 newtons. So we can see our kinematics coming back into play here. Allows us to solve for the acceleration, and if we know the acceleration and the mass, we can figure out the force that was applied. We needed 56 newtons to enable her to move away at an acceleration of 1 meter per second squared, and we have an equal and opposite force exerted on the boards.